evolution. How biopsychology tracks the inner workings of our minds. ONUR GÜNTÜRKÜN, Ruhr-Universität Bochum.
On the 9th of November 1989, I was in Konstanz and watched the events on TV. I was in tears of happiness.
Ladies and gentlemen, I will talk about our brain and our intelligence. I will talk about brains that are possibly better constructed than ours. And then finally, I will talk about the dinosaur in your living room, okay? That's the program. Let's start. How does cognition and intelligent behavior emerge in our brain? Well, we neuroscientists have an answer. Just look at the human brain that you see on top. Most of what you see is the cerebral cortex. Let's look a little bit into it. And what you see is this beautifully six-laminated structure of our cortex. If we zoom a little bit deeper, we can see the blueprints of our cognition. What you see are two orthogonal streams of information processing. The vertical lines represent the perceptual input that come in, and they are analyzed in greatest detail along these red lines. Connecting them are the horizontal blue arrows. They are the associative fibers. They connect everything with everything. What a beautiful machinery. We can be so proud of our brain. Everything is analyzed in detail, and everything can be connected to everything else we know in our brain. A formidable engine. So, do all vertebrates have a cortex? No. Only we humans have a cortex, while other vertebrates, like for example birds, don't. Now let's first understand what goes on in a bird brain by comparing it to the human brain. Let's first concentrate on the human brain that you see on top. In green, you see the huge cerebral cortex on top. So what is tucked in the middle, the pink structures? These are the basal ganglia. They organized automatized behavior. Imagine you drive with your car through Berlin. There's thick traffic, and you mind wander about the next Falling Wall conference. I can imagine you, for example, doing this. And you go through the traffic and nothing happens. This is your basal ganglia. You should say thank you from time to time to that. While your cortex is busy going on with the next Falling Wall conference, your basal ganglia do it, just automatized behavior. Now let's look at the bird brain that you see below. It's all basal ganglia. There is practically no cortex. That means birds might be incredibly efficient when it comes to automatized complex behavior, but they lack the cortex that is so crucial for cognition and intelligent behavior. So birds got a problem here, a real problem here. But there is a second problem they have, and that's the size of their brain. In neuroscience, we know that cognitive power correlates. It's not a perfect correlation, but correlates with brain size. This is about the size of a human brain, the melon. The fruit to the left, and I cannot name, is comparable to the brain of a chimpanzee. And now I'm a bit ashamed to show this. That's the brain of a corvid. And I have to tell you that corvids have rather big brains for a bird. So I would say the future looks dim for the intelligence of birds. That's at least what we heard in the last 100 years. That's how I grew up with. To my knowledge, this was what neuroscience has to say. But somehow I always had the feeling that this can't be the truth, because I was working in a fantastic lab with pigeons, and I'm still having pigeons in my lab. And I know what these animals are able to do. So this contrasted with what I was learning in neuroscience and what's written in neuroscience textbooks since about 100 years. So what is it that pigeons, for example, are able to do? Let's dive into the pigeon world by having some examples from the perceptual, their memory-based, and their cognitive abilities. Pigeons can easily learn to categorize all kinds of photographs that, for example, contain humans or non-humans. This guy in a workshop, bike shop is just one example. And after they learn to discriminate between human and non-human containing pictures, they can easily transfer it to new photographs. I wanted to know how they do it. My idea was maybe they concentrate on little features like the presence of a nose, an eye, or a mouse. This would imply that if I chop up the pictures into smaller and smaller pieces, they still would be able to do it because the features are there. But beyond a certain limit, they wouldn't be able to do it because the feature is too big for the little piece of photograph. So I chopped it up, level 1, 2, 3, 4, 5, 6. Believe it or not, even at stage 6, they were significantly above chance level. By telling us, yes, there is a human being, or no, there is no human being in this picture. Now you might say, okay, that's impressive, but maybe they have sharp eyes. Let's talk about memory. Pigeons can easily learn 725 abstract symbols, and this is just an arbitrary collection of these 725, and can tell for each symbol whether this is arbitrarily in the group of the positive or in the group of the negative pictures. Okay, you say they have a good memory, but that's not identical with cognition. Let's go for cognition. Would you accept learning English orthography as a part of cognition? Well, pigeons do. Just a few years ago, we had a paper together with our New Zealandish colleagues in which we could demonstrate that pigeons can learn 4-letter English words and can tell whether these are written correctly or written incorrectly. We trained them first with a couple of words, and then they could transfer it to novel instances. And you know, the cognitive strategies, by using different tools, we could reconstruct the cognitive strategies, and their cognitive strategies are identical to the cognitive strategies British children have when they learn to read and write in primary school. And now comes the bitter truth for the century-old theory. This, ladies and gentlemen, this little raisin is about the size of a pigeon brain. It has no cortex, and it's very small. There must be something wrong. There must be deeply wrong with the theory that we grew up with within the neurosciences. This wall must fall. Therefore, we congregated 15 years ago at a university, Duke University, experts on this field, and we said, we are not leaving this place until we come up with a new theory on the evolution and the structure of the bird brain. And after many, many days of incredible hard work, we came up with a new theory. Now, just look at the pictures at the bottom. You've seen that before. And to the left, you see the zebrafinch brain, and you've seen that this is all basal ganglia. It's all pink. That's wrong. It's cortical tissue. But this cortical tissue is not organized in layers and columns. It's organized in a way that we still do not completely understand. But it is, in fact, mostly or even entirely cognitive tissue. So what happened during the evolution of the bird brain with the lamination of a cortex-like brain that they inherited? To demonstrate this, I could use something sweet here. Klaus, could you be of help at that point, please? Thank you. Are they fresh? Okay, that's good. Thank you very much. Thank you, Klaus. Thank you. This guy is outstanding. First he's a spy, now he's making cakes. Unbelievable. So imagine this to be the brain that birds had inherited when they started their evolution. It was already laminated, as you can easily see, and sweet. What birds did with it is this. They just destroyed it. And was still fine. So they destroyed the lamination and the the columnar organization to come up with a completely new kind of organization. We still don't know what this new organization is about, But we are pretty sure that they had a lamination in the beginning and then got rid of it because they had a better idea how to organize their brain. As I said, we still struggle with what the organization is, but we start to understand a few things about it. First, a few years ago, Brazilian and Czech colleagues have discovered that bird brains have a 6 times higher density of neurons than our brain has. That means they have a much higher number of neurons. Although they have small brains, their brain numbers, their neuron numbers, are much higher, 6 times higher than expected. That still doesn't close the gap in size that you can see, but it makes the gap at least a bit smaller. But there is a second effect, and that's the following. A few years ago in my lab, we discussed about the possibility that just by higher density of neurons, the neurons come closer to each other, isn't it? When they come closer, the distance of communication between the neurons become shorter, and so communication could be faster. So now imagine 2 groups of neurons, let's say the black and the red ones, communicate in a ping-pong style with each other, so crisscrossing information in a repetitive way for quite a while. That could imply that in this kind of cognitive operations, birds could be faster, because in this repetitive organization, then really the conduction time goes down due to the closer position of the neurons. So we came up with an experiment in which our students had to compete with our pigeons. Tough competition. And this experiment had 2 phases. In the first phase, this ping-pong-like cognition was not required. In the second phase, this ping-pong-like cognition was required. The study was done in a way that in the first phase, students and pigeons were on par, so they were of equal performance levels. But as soon as students and pigeons entered the second phase, pigeons became faster than the students were. That means, indeed, the higher density of neuron not only packs more neurons into their brain, but it could also increase, by the decrease of transaction time, their cognitive speed. That could be a part of a solution for the mystery, how birds excel in so many cognitive tasks with such small brains without a cortex. There is one thing more that I would like to add, and that's the question, are birds smarter than we are? And obviously, the answer is no, they are not. They are not because we have so many neurons that we simply outsmart by outnumbering them. So although they have a higher density, we simply have much, much more neurons than they all have. And we are the smartest animal on this planet. But what would happen if there would be a big bird-brained animal? A big bird-brained animal. We are very fortunate that there is none on this planet. But maybe a while ago, there were some. For example, this one. You might not know, ladies and gentlemen, but 66 billion years ago, when we knew the dinosaurs got extinct, they were not completely extinguished. A small branch of the dinosaur family survived. And this is not a fairy tale, this is the truth. This small branch of the dinosaur family are the today's birds. So if you go to your house and you see your budgie or your canary, be careful, it's a dinosaur. Now, I would like to draw your attention to the kiwi. This is about the size of a T-Rex brain, a bird-brained animal. So in the case you ever encounter a T-Rex, ladies and gentlemen, be careful. Not only that it's big and has sharp teeth, but it's also bird-brained with a really big bird brain. Thank you so much.